Welcome to our second week of class. This week we're going to be covering Chapter 2, so we'll have this lecture video covering the textbook slides, and then we'll have a problem-solving video going over some of the problems at the end of the chapter. So this is a lot of what we had covered in class or in lab on Friday or Saturday, depending on your section. So doing calculations with scientific notation, significant figures, and doing some dimensional analysis or unit conversions. So the first thing up is scientific notation. Scientific notation is just a way for us to write numbers in a more compact or convenient way. It's not always the way we want to do it, but when it's convenient, it's definitely convenient. It's definitely the best way to go about it in some cases. So what we do is we take any number and we break it into a decimal part and an exponential part. For the decimal part, we want to have one significant figure to the left of the decimal, and then the remaining significant figures to the right of the decimal. We can get rid of any non-significant zeros in this manner, but we want to keep all of the significant numbers in the decimal part, and then we'll use an exponential part that has the base of 10 always, and then some exponent depending on which direction we have to move the decimal, whether we make the number smaller or larger. Again, to remind us what exponents mean, exponents is just a way for us to multiply things, so we can always have something times by 1, and so 10 to the 0 is just 1 times nothing. 10 to the 1 would be 1 times 10. 10 to the 2 would be 10 times 10. We can have that 1 in there, but it kind of gets, pointless at this point. 10 to the 3 would be 10 times 10 times 10, or 10 times 10 3 times. And we can do the same thing with 10 to the inverse. Remember, an inverse power can be a positive power if we flip its relative position in the numerator and denominator. So 10 to the minus 1 is just 1 over 10 times itself, or 10 times 1. 10 to the minus 2 is just 1 divided by 10 times 10, so forth and so on. All right, so to convert numbers to scientific notation, we want to first figure out the decimal part and then the exponent part. The decimal part is just like we said. It's going to be one significant figure, the first significant figure, to the left of the decimal place. So that's 1 through 9. And then we're going to multiply that number, keeping all of the significant figures after the first one to the right of the decimal. We're going to multiply that by 10, raised to some power. So if we have 5,983, we can move this decimal place over 3 times. Since we make 5,983 smaller to 5.983, we're going to make the exponent term larger. The opposite case is where we make the number larger. So in this case, 0.0003 is much smaller than 3.4. Since we made the number, or the decimal part, larger, we're going to have to make the exponent smaller. Also, if we move our decimal to the left, we're going to increase our exponent, or if we move to the right, we're going to decrease our exponent. So, measure of uncertainty. Uncertainty is something that we don't often think about, and it's something that we have to be aware of as scientists. So, typically, when you have a digital readout, we don't have to worry about uncertainty. The software accounts for it for us. But when we're doing a physical measurement where our eye is doing the recording, so in this case of using a ruler or a thermometer or any manual readout instrument, the last decimal is going to be estimated here. So this is gradated to 1 millimeter. So we know for sure that this is greater than 24 millimeters. But we also know that it's somewhere between 24 and 25. We can't be certain, so we have to estimate it. This estimation doesn't have to be perfect. If you looked at this and estimated it slightly different, you said, oh, that looks like 24.5 exactly, or 24.7. That's all fine. That's perfectly acceptable. We just want to get an idea of, is this closer or further away from 24? Is it closer to 25, or is it somewhere in the middle? Is it right in the middle? Is it kind of skewed one way or the other? It's just to give us an idea of which way the measurement is heading. So what this means is, we could take this example from the book. Average global temperatures have risen by a little bit over half a degree in the last century. However, we can only measure these global temperatures within plus or minus 0.1 degrees Celsius. So we don't know that it's exactly 0.6. We can give kind of a range that, due to the instrumentation that we have available, it's somewhere between 0.7 and 0.5 degrees Celsius. And because we have a level of certainty below one whole unit, we can tell these to plus or minus 1. We wouldn't want to round this all the way up. We'd lose a lot of information from that. However, we can report this as a range, and that's typically what we would do in science. So if we were reading a number off an instrument or from a report, not something that we did ourselves, we would know that everything up until the last decimal place, and if this was a whole number like 560, we would take it up to the last significant figure. That last significant figure we know is an estimate. Everything before that last digit is going to be exactly known, but everything that last digit will be an estimate. So here's another case where you would have to estimate your last digit. This gram scale is a manual readout. This is very similar to what you would have in a kitchen scale, not typically what we would have in a laboratory. However, you might have a setting where you would have to use this type of instrument. We would read to the individual thresholds. We know that it's at least 1 gram. That's what that first marker. We could count all these ticks to figure out how much the gradation is set at. There's 10 ticks between 10 and 0, so each tick is 1 gram. It's slightly over 1 gram, so we want to give some indication of how much it's over. It's just barely over 1 gram. So we could say it's 1.2, 1.3, 1.1. Any of those would be fine. You wouldn't want to call that 1.5 because it's clearly not in the middle of those two ticks. So it's definitely closer to 1 than it is 1.5 or even 2. So that's all we're doing with these estimates, is just trying to get in the right direction of a more accurate measurement. Here's a more complicated scale. You might actually use one of these if you're balancing something against a known standard. So if you had something that weighed exactly 1 gram, you could calibrate the scale with something like this where you have a fine-tuned measurement. We see the large gradations here are 1 to 2. You can see 3, 4, 5. In between here, there's 10 ticks, so it's broken up into tenths. We could then estimate the hundredths place from here. It's a little bit over halfway, so in the hundredths place, we could say it's about 0.6 or 0.7, depending on how you interpreted that distance. So, significant figures. We talked a bit about this in class on Friday and Saturday. But just to remind us, all non-zero digits are significant. So 1 through 9 are significant. Zeros that are sandwiched between significant numbers are significant, like 101. The 0 in 101 is significant. Trailing zeros, numbers that are to the right of a decimal place but also have a significant figure somewhere to the left of them, are significant. So 1.0. That 0 to the right of the decimal is significant because it has a significant figure somewhere to its left. So 100 only has one significant figure, but 100.0 would have 4 significant figures because that 0.0 is to the right of the decimal and has a significant figure somewhere to its left, a 1. And those zeros between 1 and the decimal place now become significant because they're sandwiched between 2 significant figures. Okay. Leading zeros. Leading zeros are not significant. What is a leading zero? It's a zero that does not have a significant figure to the left of it. That's as simple as it is. So 0.000001 only has one significant figure. All of those zeros preceding it are not significant. Trailing zeros is something the book talks about as being ambiguous. If it's given to you in a textbook or written for you in an academic setting, you don't assume anything's ambiguous and you use the 5 previous rules. If you're dealing with the real world, looking at someone's laboratory notebook, that's where it's more ambiguous. And if necessary, you just talk to the person who made the original note for clarification. In a laboratory setting, there's no ambiguity. Follow the previous 5 rules. So, exact numbers. Exact numbers are pretty hard to come by and pretty much For our sake, exact numbers are conversion quantities or conversion factors. So down here at the bottom, we have 1 inch equals 2.54 centimeters exactly. We have set, as a scientific community, 1 inch to be exactly 2.54 centimeters. Now, centimeters are related to meters, which have a fundamental derivation that we'll talk about here in a second. But if we have exact significant number, or we have an exact number, we have infinite number of significant figures, we can't be any more precise. All right, so let's do a little practice and count significant figures. So in this first example, we only have 2 significant figures because these leading zeros are just placeholders. Now in the next case, we have a significant figure to the left. So these zeros to the right, this 0 right here, it's not a leading 0. It's a significant 0. It's exactly 1.080. We have confidence up to the thousands place. So every digit in here is significant. All non-zero numbers, all of them are significant. The book kind of goes back and forth on this, depending on what slides and what part of the book you're looking at. Significant figures for scientific notation are always determined by the decimal part or the numeric part. So there's 3 significant figures here. We treat 10 to the 5 as a conversion factor. That's how we convert from 2.97 to 297,000. That's the conversion factor, 10 to the 5th. So we consider this as having infinitely many significant figures. Remember, when we do multiplication, we select for whichever one has the least number of significant figures. Since this has 3 significant figures, our answer is 3 significant figures. 1 dozen equals 12 is a conversion factor, so we would say it has infinite number of significant figures. 100.00, this decimal place and the zeros tell us we know this exactly to the hundredths and tenths place. So that means that the zeros to the right of the 1 are also significant because they're sandwiched by significant figures. The book would say 100,000 is ambiguous. I would argue that you're not going to be presented situations in this class that are ambiguous. That's only in real world scenarios where you have ambiguity. And if you have ambiguity like that, instead of writing the number as 100,000, if you had 6 significant figures and your answer just happened to be 100,000, you would write it as 1.00000 times 10 to the 5th. Kind of similar to up here, just with a 1 and a bunch of zeros. All right, so when we do calculations, we have to round numbers. And so the general rule for rounding numbers is wherever our significant figure is, we cut off after that significant figure. The next number determines how we round our last significant figure. If that number that we're using to round is above 5, we round up. So 5 or above, we round up. 4 or below, we round down. So what does this look like? So if we had 2.33, and we only had 2 significant figures, we'd go 2.3. Okay, that's 2 significant figures. We'll use this second 3 to determine how we round. 3 is less than 5, so we round down to 2.3. However, if we had 2.37 under the same circumstance, we would use the 7 to round. 7's 5 or larger, so we'd round up to 2.4. Multiplication and division is kind of the easy significant figure rule. We count how many significant figures we have in all the numbers that we're doing a multiplication or division operation with, and we select for whichever one has the lowest number. So if I multiply 2 times 101 times 1.235497, the first number I said was 2. That's only 1 significant figure, so I have to round my answer to 1 significant figure. I'm going to keep a bunch of extra decimal places during my intermediate calculations, but that's just to make sure that my answer is accurate as possible. We're going to then just remember how many significant figures we have in the intermediate calculations, and at the end of the day, we'll round to however many significant figures we have. So in this case, we have something with 3 significant figures, 5 significant figures, and 2 significant figures. We'll keep all the decimal places for the intermediate calculations, but at the end of the day, we're going to have to round to our least number of sig figs. So 2 sig figs here. This leading 0 is just a placeholder, so we'll get 45 at the end of the day. Same thing here. Division and multiplication are the same. They're just kind of opposites. So we have 4 sig figs and 3 sig figs. We'll use all of our intermediate or all of our decimal places for an intermediate calculation, but we have 3 sig figs, so we'll go 1, 2, 3. This is the last digit we'll keep. 9 is greater than 5, so we'll round up to 0.966. Addition subtraction is the more tricky one, where we want to align our numbers on the decimal place and then select for whichever one has the least specific information or the fewest decimal places here. So in this example, 5.74 tells us less information than either of these other numbers. These other numbers are more precise. They tell us information to the thousandths place. Since we can't know or we don't have confidence about the thousandths place on 5.74, we have to use a cutoff line at that place that we have confidence up to. We'll cut off right here and then use the next digit after we cut off to determine how we round. So we just plug this into our calculator, realize we have 3 significant figures, or we have to cut off at the hundredths place. We cut off after the hundredths place. We use the thousandths place to round. 4 is 4 or less, so we round down. Again here, 3.965, we have 4 significant figures. We have confidence up to the thousandths place. But 4.8 is 2 sig figs, and we only have confidence up to the tens place. Since we only have confidence up to the tens place, we have to use the number that we're least confident in. So we cut off right here after the tens place. 3 is less than 5, so we round down to 0.8. So when we have mixed addition and subtraction, what we want to do is we want to follow our order of operations, our PEMDAS. Parentheses, exponents, multiplication, division, addition, and subtraction in that order. We want to keep as many decimal places as possible for our intermediate calculations without rounding. We're going to remember how many significant figures we have for every operation, and at the end, we'll use either our multiplication and subtraction, multiplication and division, or our addition and subtraction rules to determine how many sig figs we have at the end of the day. So let's take a look at 3.489 times this subtraction problem. So since the subtraction is in the parentheses, we're going to do that first. We'll align along the decimal. Since the decimal for 2.3 is cut off at the tenths place, and we have information up to the hundredths place on the other one, we're going to use what's in the hundredths place to round. Since we get 3.37, we would round up, but this is an intermediate calculation, so we're just going to remember that we have 2 significant figures. We have 2 significant figure number multiplied by something with 4 significant figures. We're going to select for 2 significant figures because that's the least number of significant figures that we have. And at the end of the day, we'll round our answer to 12. So we are going to primarily use the metric system. There might be some homework problems with the American Standard, but I won't give you anything like that on exams or quizzes. Maybe I'll give you something in Fahrenheit and ask you to convert to Celsius, but I'll give you the equation for that. So we really want to get familiar with the metric system. International System of Units. It came from the French. I'm not going to try to butcher it, but that's why we call it SI units. Now we just call it metric for the most part, but here are all the base units for some of the metric quantities. You'll notice that the base unit is not always the unit base. And what I mean by that is meter doesn't have any prefix, but kilogram has a kilo prefix. And so that's not the base unit. The base unit would be gram. However, the SI base unit is the kilogram because that's the most useful unit. Most things over the years have been calculated in kilograms, and it just makes more sense based on our societies and evolution to use a kilogram than a gram or a megagram or any other given unit. But typically the SI base unit is the base unit. There are a few exceptions. We'll talk about this as we reach them, but in general, the base unit is going to be whatever I give you your constants in. So we'll get a couple constants for fundamental equations. They'll always be given in the base unit, and so those will be given on your equation sheets. Just use those for your reference. So we said that a little bit earlier that the units we like to base them on fundamental properties, and so in 1983 we were able to, use a experimental setup to calculate how far light travels in a vacuum in 1 second. And so we decided to set the meter to this exact one 299,700 or 299,792,458 seconds, inverse seconds. Because it's basically 1 over the speed of light is what a meter is equal to. So no matter where we are in the universe, we can always replicate this. And so rather than a meter being based off what some random individual says a meter is, we can correlate it to a fundamental property of the universe. And this is what we'll do for a whole bunch of the standard units nowadays. You don't need to be concerned with this. It's just something to be aware of. This is how we determine what units actually are nowadays, rather than just arbitrarily setting them according to what we think they should be. So this is how we would define the kilogram. Again, not important, kind of interesting, but beyond that, not really useful. For time, for a second, it's the half-life of, a radiation of a cesium-133 atom. So we want to talk about the difference of weight and mass. This is very important for a physics class, but we'll touch on it since we're talking about units and measurement. It's appropriate. Weight is mass times gravity, whereas mass is the amount of matter within an object. Mass does not change anywhere in the universe. Weight is dependent on the gravitational force of the object is feeling. So on Earth, the difference between the lowest point on the Earth's surface and the highest point on the Earth's surface is so minimal that weight and mass don't really change anywhere on Earth. What we can measure as mass is the same as weight. There's minor differences if you go to the top of Mount Everest and the bottom of Marianas Trench, but it's so minuscule that we can essentially equate them to be the same on Earth. However, once you start talking about, different gravitational forces and different places in the universe, things in vacuum, then mass and weight are not the same. We're not going to really deal with this, but it's something that you should be aware of. So I drew this kind of style of a table up on last week's lab class. You're going to have something very similar to it on your exams for you to use as a metric conversion chart. You should be familiar with these. I will give you one on the exams, so don't worry about memorizing them. Just be familiar with how to convert between all of them. Again, this one doesn't have the base unit, but the base unit has no prefix and it's just equal to 1. We can set these things equal to each other, or if you're not comfortable, converting from one prefix unit from like kilo to centi per se, you could go from kilo to the base and then from the base to centi using these charts. Again, we'll practice, but in general, we want to choose a prefix multiplier that makes sense for what we're dealing with. So if we're dealing with atoms, we're probably going to use nanometers or picometers if we're being really particular. If we're talking about things in biology, we're probably going to use millimeters or micrometers. If we're talking about things in the universe, we're probably going to use kilometers or megameters or something very, very large. So volume is a dimensioned unit, so it's basically some distance in three-dimensional space. So up and down, left and right, forward and back. Those are kind of our 3 independent directions. If we have a measurement in each 3 independent directions, we have a volumetric measurement. And so we can say volume, which is typically liters or milliliters, is equal to cubic centimeters. So milliliters is equal to a cubic centimeter. We can relate the cubic distances to liters and other volumetric terms. So something that you might have to do, I've already mentioned one of the challenge questions involves using density of a cube. that density might be given to you in cubic centimeters, and you might have to give the answer in liters. So that requires a couple conversions. So unit conversions are the most important problem solving skills you can have in this class. It's what you're going to use for almost every problem. There will be a couple problems where you can kind of just plug and chug into an equation, but for the most part, it's going to be some type of dimensional analysis where we have some starting point and we want to convert that starting amount of something into some other quantity, whether it's atoms of chemical A into molecules of chemical B, or whether it's grams to kilograms to pound, we're just converting quantities from one to another is the biggest math we're doing in chemistry. So we'll keep going. So using dimensional analysis, the most important thing with dimensional analysis is you have some unit you're starting with. In order to get rid of that unit, you need to divide by that same unit or multiply by a new unit divided by your current unit. So we have a given unit. We want to cancel out whatever given unit we have. Hopefully we can go directly from our starting unit to our desired unit, but sometimes this is a multi-step pathway. We have to convert one to another, and finally we can get to our desired unit. This is a simplified, diagram, but this is the goal, is to do one single conversion to get to our desired unit. Remember, whatever we're trying to get rid of needs to be in the denominator, unless our given unit happens to be in the denominator too. So if we had something like meters per second and we wanted to convert to meters per hour, since seconds is what we're trying to get rid of, that's in the denominator, we would want our given unit in the numerator, the opposite of what we're seeing here. So we have conversion factors. This is why conversion factors have infinite sig figs. If we take 2.54 centimeters divided by 1 inch, that's exactly equal to 1. 1 doesn't change anything. So we can always multiply or divide by 1, and we don't change our answer. We just convert from one unit system to another unit system. So in here, if we had 44.7 centimeters, we could divide or multiply by 1 inch over 2.54 centimeters, or just divide by 2.54 centimeters. We cancel out our centimeters term, and we're left with just inches. This is exactly equal to 1, and so we might be changing the number along with the units, but this is the exact same quantity, so we're going to keep the exact same number of sig figs. We started with 3 sig figs, we multiplied it by something with an infinite amount of sig figs so that we could convert the units to something more approachable or more palatable. We keep the same amount of sig figs or the same amount of information. So again, here's just some more algebra that we've covered. Hopefully you're comfortable with fractions and kind of multiplying or dividing anything and everything by 1. You can also raise everything to the 1th power if you feel like it. So a solution map is a good idea for when you're learning how to do dimensional analysis. What a solution map is it's your starting point, your end point, and the steps you're going to take in between to get there. So most of the time with these early problems, they'll just be a one-step conversion. So your solution map is kind of trivial. But if you have to do multiple, 4, 5, 6 different conversions, having this solution map of, okay, I'm going to go from A to B, B to C, C to D, so forth and so on, is a very good idea because you can catch any mistakes. It's also important to keep all your units so that you can, have good bookkeeping. So a solution map would look something like this, where I'm starting with inches. I want to go to centimeters. Luckily, this is just a one-step conversion, so I have one intermediate that I have to go through. That's this 2.54 centimeters per 1 inch conversion. Since I started with inches, I want inches to be on the bottom so that they'll cancel out. If I was doing the opposite case, I would want to flip my conversion so that inches is on the top, centimeters is on the bottom. Centimeters is what I'm starting out with. They can cancel out, and I'll get inches at the end of the day. This is very trivial when we have simple problems, but when you have 5, 6, 7 step conversions, it can be a lot more useful, kind of a bookkeeping method. So you always want to start with what you're given, and then identify what you need to find and see what path you can get that will get you there. There's not one correct answer. You can start and go different places. It's up to you. There's usually a quickest way, but there's not only one way to do this. So, in general, given, use a solution map to kind of bridge the gap to what you need to find. So, you can take a look at the book's recommendation for doing these. We'll do some problems like we did in the lab class as well. So here's a more complicated example where we have 2 steps. We want to go from centimeters to feet. We don't know that we have to go to inches right off the bat, but the first thing we're going to do is we're going to look at our conversion sheets and go, I don't have anything that takes me directly from centimeters to feet, but I do know that feet and inches are related by this conversion factor. Oh, and then I can use this other conversion factor that relates inches and centimeters. So I can use this as, from A to B, I have to multiply by this factor. My centimeters will cancel out. I'll get inches. From B to C, I need to multiply by this conversion factor, so my inches will cancel out. And then I'll get my feet at the end of the day. You can group these conversion factors together if you want, but for clarity of your work, it's probably best to keep them separate so that you can track every step in the dimensional analysis. So in this case, if we had 194 centimeters, we could use the conversion factors as we said, making sure that centimeters cancels out with centimeters, then inches cancels out with inches, and we're left with feet at the end of our answer. We have 3 significant figures in the starting number. We have infinite number of sig figs in our conversion factors. We'll keep a bunch of decimal places in the intermediate calculations, but at the end of the day, 3 significant figures is the least number of significant figures in any of the multiplication operations. So we're going to round to that. 4 is the 4th place, so we keep 1, 2, 3. This 4 is 4 or less, so we round down to 6.36. Here's another one. So if we wanted to go from miles per gallon to kilometers per liter, if we were wanting to go from maybe a more American standard measurement to a European measurement, or really what the rest of the world uses other than us, this is how you could do it. We figure out how many kilometers are in a mile. Miles cancel out. Then we want to figure out how many liters are in a gallon. Since gallon is in the denominator, we're going to want our conversion factor to be in the numerator. Gallons will cancel out and we'll be left with liters, and we can convert 48 miles to gallon to 20.4 kilometers per liter. We started with 3 sig figs. We multiplied by 2 conversion factors that have infinite number of sig figs. They're exactly these quantities. And so at the end of our answer, we're going to have 3 sig figs. So you can use either the numeric, so to scroll back, you can feel free to use either the multipliers or the exponential term. This feels more safe when you're getting started out. However, there's a lot more work into putting this into your calculator and a lot more chances for error. I would recommend that you get comfortable using the exponential notations to convert your units. It's going to be a little bit more difficult at the start, but it's going to save you a lot of headache at the end of the class. All right, so trying to get back to where we were. Okay. So, we can do dimensional conversion factors. So we've seen this a little bit. We have cubic centimeters. Well, we know what a centimeter relates to an inch, but we don't really know offhand what a cubic centimeter to a cubic inch is. And I'm not going to give you those conversions because they're pretty rare. And ultimately, all you need is the linear conversion factor, the one that isn't raised to whatever power, the square or to the cube in this case. You can devise these or derive them yourself by just cubing every side. Whatever I do to one side of the equation, I have to do to the other side of the equation. It always has to be fair. So if I cube 2.54 centimeters, I have to cube 1 inch. Now that just gives me 1 inch cubed because 1 cubed is just 1, but it gives me a pretty large number over here. And so the conversion factor for dimensional conversions versus linear conversions, squared or cubic conversions, are going to be much larger. And so that's just kind of a logical check for you to realize your answers they should increase quite a lot when you're dealing with dimensional or volumetric units. So density, we kind of went over this during the lab. Density is mass over volume. You'll be given densities and expected to figure out what the mass or what the volume is of something. Or in experimental sense, you'll have to measure out so much mass of something, but you only have it in a liquid form and you have to do it volumetrically. You can use the density multiplied by the volume to figure out the mass. Or the mass divided by the density to figure out the volume. Rearrange the equation however best fits your needs. So in this case, if we wanted to calculate density, sometimes it's really easy. If we're given mass and we're given volume, well, density is mass per volume. We take the mass, we divide by the volume, and we just leave it as is. If the units are not specified, we can put them in whatever units we want to. Now, typically the units will be specified and we might have to do a unit conversion. So we can think of this equation as a conversion factor. The density is just mass over volume. It's grams per liters or grams per milliliter, kilograms per centimeters cubed, whatever unit we want to use. We can also, flip this around. The inverse of density, or the 1 divided by density, is equal to volume over mass. We can use these interchangeably. So if I was given how much mass I needed and I had the density, I could figure out how many milliliters or how many cubic centimeters I had to measure out with a volumetric device. And so we would take the density. We have grams. Since we want to go to volume, we're going to need to divide by grams. Grams per centimeter, grams is in the numerator. So we divide by that, or multiply by the reciprocal. 1 centimeter cubed per 1.32 grams is our conversion factor. We multiply by that, and now we have centimeters cubed. However, we want to do milliliters. We can't measure out a centimeter cubed, really. That's kind of difficult. You would need an actual cube to measure it out with. We usually have cylindrical devices that are measured in milliliters. So we would do the 1-to-1 conversion. 1 milliliter equals 1 centimeter cubed. And then we could convert our answer to milliliters. If we did this, grams would cancel out, centimeters cubed would cancel out, and we'd be left with 51.8 milliliters, noticing that we have the same amount of sig figs as we started with because we don't change our number of sig figs because these conversion factors have an infinite number of sig figs. They're just exactly equal to 1. They don't change our confidence in this measurement at all. So I don't expect you to memorize densities. I expect you to get a chart similar to this and be able to use it to calculate problems. I'll tell you what the density is, or I'll give you the information to calculate what density is. I think for the first exam, I might give you the formula, density equals mass over volume. That should be something that you can figure out because the units of density are essentially the equation. Mass, grams is mass, centimeters cubed is volume, density equals mass divided by volume. So very simple derivation that you guys should get comfortable with. So here's some more examples. Titanium, lighter, or elements that come earlier in the periodic table tend to be less dense than elements that come later in the periodic table. These heavier elements tend to be more dense. Lead is pretty dense and very cheap. And so that's why we use it to protect from radiation, is it's so dense that it actually absorbs and reflects and prevents any radiation waves during diagnostic imaging from reaching parts of our body that would be detrimental or that we just wouldn't want to have that exposure to. So we talked about uncertainty. You should be aware that you need to estimate the last digit, or that the last digit is an estimate when you're reading numbers. We only make this estimation when we physically read an analytical tool. So like a pipette, a burette, a volumetric device where we're physically reading it. Anything with a digital display is estimating the last digit for you, and you don't have to worry about it. It's only when your eyes are responsible for recording the measurement, not some device with software that spits out a number. So rulers, thermometers, those are the types of things that you're going to estimate the last digit of. Units, you need to be comfortable with your units. I will give you the unit conversions, but you need to know how to use the charts. Density, this will be part of the challenge question that we'll go over in the problem solving session. Be familiar with it. It's going to be useful in all of your science careers. And again, just to remind us, the key things that we want to be focused on in this chapter are scientific notation, significant figures, and dimensional analysis. I will see you guys in class this week, and hopefully you will get a chance to review this video and the problem solving video before then. Until then, have a good week.